Welcome to Off by 1 squared. There are lots of polygons for which we know the formula to find the area. Perhaps the simplest is the rectangle with side lengths a and b. It doesn't matter how the square is oriented, the area is always a times b. If a equals b, then we have a square, and the area is simply a squared. In this way, it's easy to see why we call raising a to the power of 2 squaring a. Other well-known formulas are the area of a right triangle with one side a and the other side b. In fact, the area of a right triangle is a special case of the area of a general triangle with base b and height h. As long as the triangle has base b and height h, its area is 1/2 h times b, even if the top of the triangle isn't over the base. There are a variety of different formulas depending on what information we have about the triangle. For example, side angle side. Here, the area is 1/2 ab sine theta. If we consider a regular polygon, it's easy to imagine splitting it into triangles whose bases sum up to the perimeter of the polygon, and the area is then the sum of the areas of all of the triangles, or just 1/2 times the perimeter times the height of each individual triangle. This height is known as the apothem. But what if the shape isn't regular? As long as it is non-self-intersecting, that is, simple, there is still a really easy way to compute what's termed as the signed area of the polygon. First, we have to label each vertex, and we'll do so in the positive orientation, which is counterclockwise. You'll see that the math makes this a positive area, which is why it's called the positive orientation. Let's label the vertices x0, y0, x1, y1, etc. You'll notice that since there are n vertices, the last will be x sub n minus 1 and y sub n minus 1. For convenience, we'll also set xn and yn to be the first vertex. That is, xn is x0 and yn is y0. The basic idea to find the area here is to consider that we can easily build a trapezoid for each edge in the polygon. It's not hard to show that the area for such a trapezoid is the average height times the width. In this case, the area is 1/2 of y0 plus y1, which is the average height, times x0 minus x1, which is the width. Let's consider an explicit example. Here, 1/2 y0 plus y1 is 1/2 9 plus 11, or 1/2 20, which is 10. x0 is 12, and x1 is 9, so x0 minus x1 is 12 minus 9, or 3. So the area of the first trapezoid is 30. You'll notice that we've added too much area here, because we added all the area under the top edge, but that includes the area under the polygon as well. Remember when I mentioned positive orientation? Here x1 is less than x0, so by subtracting x1 from x0, we get a positive area. But as we move counterclockwise along the top of the polygon, we keep adding up too much area, all the area under the polygon. Now we get to the left side. When we add the next polygon, note that x sub I is less than x sub I plus 1, so using our formula, we get a negative number. And this is what we want, because if we add a negative number, we're subtracting away some of the polygon that we had overmeasured earlier. We'll leave this in blue to show that we've subtracted it, but the current area is just the area in red. This next section does two things, neither of which we want. It overcounts an area, which we show here in pink. This area had already been counted, but we're counting it again. But we also added back in an area below the polygon that we had already removed earlier. But that's okay. Now as we move back to the right, we're subtracting areas, and we see that we subtract both the area below the polygon which we had added back in, as well as this area we had double counted. So we go back to having counted it exactly once. As we finish going around the polygon, we see we have counted the area inside the polygon exactly once, and nothing outside the polygon. We added some areas up too many times, but if we did, we always subtracted out what we overcounted later. So we see we've actually now only counted the area shaded in red. What's left in blue is just to show what we had counted but have subtracted off. Thus, if we put this all together in summation notation, we arrive at the trapezoid formula for the area of a polygon. There are a few other ways this can be written, but I actually want to dive into some different math to approach finding the area in an entirely different way. Remember when I said the simplest polygon to take the area of was a rectangle? In this approach, we're going to approximate the area of the polygon by summing up lots of rectangles. You may be familiar with the concept of a Riemann sum, generally introduced in a calculus course to show the approximation of an area under a curve, the limit of which becomes the integral. We won't be getting into that in this video, but we'll take these same ideas and see how we can apply them to our polygon. The basic idea is that we want to subdivide our polygon into rectangles and add the areas of the rectangles. Let's see how we might fit one in the middle of the polygon. This rectangle's width is 5 and its height is 2, giving it an area of 10. But this leaves a lot to be desired. For one, it's obvious that this rectangle underestimates the area. For another, we have no idea how to even get this rectangle. Do we have to solve for intercepts of lines? How do we pick these coordinates? At first glance, it looks almost insurmountable. Once we've picked one rectangle, we have a bunch of the polygon left, so we need to pick more rectangles. And this process goes on and on. Let's go at this from another angle. It's easy to find the smallest x-coordinate of the polygon, here. Similarly, the largest x-coordinate is here. Likewise, the smallest y-coordinate and the biggest y-coordinate. Using these, we can easily find a rectangle that fully surrounds the polygon. And it's easy to measure the area here, but let's not get ahead of ourselves. Instead of measuring that and then trying to keep finding smaller rectangles to remove, which would still be hard, let's find some simpler things we can do. The easiest thing we can do is subdivide this rectangle into 4 new ones. But now what? Well, what we'd like to do is fill our polygon with rectangles that are fully inside the polygon, and which we know the area of, and then just add all those areas up. Let's see how this will work. Let's look at R1. We see that some of this rectangle is in the polygon, and some isn't. So let's subdivide R1 again. Now we see that R8 is fully inside the polygon. Also, we know that the coordinates of 2 opposite corners of this rectangle, so we can easily compute its area. Now we're done with R8, and as this is the first rectangle we found fully inside the polygon, it's our first approximation of the area of the overall polygon. If we further divide R5, we see one of the new rectangles formed appears fully outside the polygon. So we're done with R9. We neither count it nor divide it further, we just discard it. It's easy to visually inspect the remaining rectangles and determine they're neither fully inside the polygon nor fully outside the polygon. But we want a way to determine this quickly, using math, not having to specify each one. Let's go back to R1. We can clearly see part of it is inside the polygon, and part of it is outside. But how do we mathematically determine that? It turns out it's pretty simple. If any edge of the polygon crosses an edge of the rectangle, we know that part of the polygon edge will be inside the rectangle. This means that part of the rectangle is inside the polygon, which is on one side of the edge, and part of the rectangle is outside the polygon, which is on the other side of the edge. So how do we tell if one edge crosses another? We'd like to know if the line segment between A and B crosses the line segment between P and Q. We can determine this using the cross product between vectors. Consider the vectors A and B. The cross product between two vectors A and B is given by the formula A cross B equals the magnitude of A times the magnitude of B times the sine of theta times n, where n is a unit vector perpendicular to the plane containing A and B, with direction such that the ordered set ABN is positively oriented. Note that theta will always be between 0 and pi, so sine of theta is always non-negative. That gives an orientation between the two vectors. As shown here, to move from vector A to vector B, you have to rotate in a counterclockwise direction, which is generally considered a positive angle. But even if we have to rotate clockwise, we still consider this a positive angle for the math, but the unit vector will be in the opposite direction. In our case, the plane containing A and B is the xy plane, so the unit vector perpendicular to the plane will always be either 0, 0, 1 or 0, 0, minus 1. That is, it only has a component in the z direction, and it is either positive 1 or negative 1. This simplifies things a bit for us. Let's see how. Let's consider the positively oriented orthonormal basis of ijk, where I cross j equals k, j cross I equals minus k, j cross k equals I, k cross j equals minus I, and so on, along with the linear independence of I, j, and k, implying that I cross I equals j cross j equals k cross k, all equals 0. We can equate I as the x direction, thus I equals 1, 0, 0, j is the y direction, or j equals 0, 1, 0, and k is the z direction, so k equals 0, 0, 1. Then we can write a as a sub 1 times I, plus a sub 2 times j, plus a sub 3 times k. And similarly for b. Then a cross b, using distributivity and linearity of the cross product, is given by this expression. And using our rules earlier, this simplifies to this expression. And again, if a and b are exclusively in the xy plane, this will be in the z direction, which means it will only have a value in the k component. Thus, we get our final simplification of a cross b equals a1 times b2 minus a2 times b1, k. So what does this mean? If we take a cross b, we always take the direction of the smaller angle to go from a to b. If this is in the counterclockwise direction, a cross b has a positive value in the k direction. But if b goes too far away from a in the counterclockwise direction, it's actually faster to go in the clockwise direction. In this case, a cross b has a negative value in the k direction. Let's go back to our problem of determining if two line segments AB and PQ cross. Consider the vector AB cross AP. Note that the shorter angle to get from AB to AP is in the counterclockwise direction. Counterclockwise means that the cross product here will have a positive k component, or be in the positive z direction out of the screen towards the viewer. Conversely, because we need to rotate AB in a clockwise direction to get to AQ, the cross product between AB and AQ will have a negative k component, or be in the negative z direction into the screen away from the viewer. Thus we see that if the sign of the k component of the two cross products is opposite, the points are on the opposite side of the line. However, if P and Q are on the same side of the line segment, AB as in here, then we see that AQ and AP are both in the same direction from AB. Thus their cross products will have a k component with the same sign and both be in the same z direction. Let's go back to when we knew PQ crosses the line established by A and B. That doesn't necessarily mean that PQ crosses the line segment AB, as we see here. Here, A and B are on the same side of the line PQ, but that tells us exactly that all we need to do to determine if the line segments cross is to check both that P and Q are on the opposite sides of AB, and that A and B are on the opposite sides of PQ. If both happen, the line segments themselves cross. Thus we need to measure the cross product a total of 4 times, once between AB and AP, and between AB and AQ, then again between PQ and PB, and between PQ and PA. Let's take an example. Let's put A at the origin, and B at 3, 0 along the x-axis. Let's consider a case where they cross. Here P equals 1 minus 1, and Q equals 1, 1. So we have AB equals 3, 0, 0, or 3i, and similarly AP equals 1 minus 1, 0, or I minus j, and AQ equals 1, 1, 0, or I plus j. Then AP cross AP equals 3 times I cross I minus 3 times I cross j, which simplifies to just minus 3k. Similarly, AB cross AQ equals 3 times I cross I plus 3 times I cross j, or plus 3k. Clearly these have opposite signs, so we know that PQ crosses the line established by AB. The other direction will have us looking at PQ cross PA and PQ cross PB. PQ equals 0, 2, 0, or 2j, and PA equals minus 1, 1, 0, or minus I plus j, and PB equals 2, 1, 0, or 2i plus j. PQ cross PA equals minus 2 times j cross I plus 2 times j cross j, which simplifies to 2k. Similarly, PQ cross PB works out to be minus 2k. Again, these are opposite signs, so we know that AB crosses the line established by PQ, establishing that the line segments AB and PQ cross. I'll leave it as an exercise to you to play with other values of A, B, P, and Q to see what happens when they do and do not cross. Going back to our polygon, we take the original bounding rectangle. We know this rectangle surrounds the polygon, so it's neither inside nor outside fully, so we know that we have to subdivide it. This is the single special case we start with because no edges cross, but we know by construction it may contain area outside the polygon. Actually, if the original polygon is a rectangle oriented with sides parallel to the axes, this original rectangle will exactly match the polygon, but we'll ignore that special case. It's very easy to detect and account for specially. So the first thing we'll always do is split the bounding rectangle into 4 subrectangles as before, R1 through R4. We'll keep those in a list and process them in order. At each step, we'll look at a rectangle and determine if it's fully inside, fully outside, or both inside and outside the polygon. If it's fully inside or outside, we'll add it to the area or ignore it as discussed before. If it's both, we'll subdivide it and add the new rectangles to the end of the list. This way, we process the biggest rectangles we have before moving on to smaller ones. As we subdivide our polygon, we're adding up an area that comes closer and closer to covering the whole polygon. We can stop whenever we want, and we can add up the areas of the remaining rectangles to be considered. We know it's possible some part of that area may be part of the polygon. In fact, we know that the area between what we have measured and the true value lies somewhere between 0 and the total area of the remaining unclassified rectangles. We can use this to decide when to stop. For example, maybe we stop when the total possible error is less than a specified fraction of the area we've measured so far, perhaps 1%. But wait, we still have one more piece to this puzzle. How do we know if a rectangle is fully inside or outside the polygon? We already know if it is one of these, because no edge crosses any edge of the polygon. But which is it? Well, we already have the tools to determine this. This topic contains some more advanced components than we'll cover in detail here. Perhaps that'll be a topic of a future video. But the key here is the raycasting algorithm, sometimes known as the crossing number algorithm or even odd rule. The idea is you take a point and go in any given direction and count how many times you cross an edge of the polygon. If you only cross it one time, you must have started inside the polygon. Likewise, if you crossed it 3 times, you started inside, went outside, back inside, and then back outside. In general, if you cross an edge an odd number of times, you started inside. It relies on the Jordan curve theorem, which states that every plane simple closed curve, that is a Jordan curve, divides the plane into an interior region and an exterior region, precisely the concept of inside and outside the polygon we've been using informally. Finally, if you cross an even number of times, you started outside, went inside, and back outside a number of times, possibly 0. There are some potential edge cases to consider, like what happens if you go through a vertex, which we won't consider here, but to make this a rigorous algorithm, they would need to be addressed. But we have now developed an understanding of how to generate a Riemann sum approximating the area of a polygon that is represented as a list of coordinates. I hope you enjoyed this dive into finding the area of a polygon. We covered an exact method, using the trapezoid formula, but then also took a more calculus-oriented approach, where we got to really understand some applications of cross products of vectors and use them in measuring the area of a polygon as a Riemann sum. If you learned something, feel free to leave a comment. If you enjoyed this, feel free to like and subscribe, and share with anyone else you know who has a love of mathematics, and let me know what else you might be interested in. Thanks, and see you in the next video.